You may hear voice of God if somebody's in. Okay, so welcome everybody. Today we're very happy to have Maciej here, who's going to tell us about surprising properties of cold black holes. Take it away.
Thanks. So today I will tell you about a few things I've done with black holes with very low temperature. There was a lot of activities in the topic in recent years, and I will stick today to stories that are either entirely classic or semi-classic. And there are various quantum effects that are also very important for near-extremal black holes, but they become important, usually they become important at temperatures which are significantly smaller than the regime of temperatures I'm going to talk about today. So these would be sort of the first type of effects you would actually see before you would go to proper quantum gravity regime. And let me start by some introduction, telling you what I mean by cold black holes. So black holes have temperature that geometrically is given by the surface gravity of these black holes, and this is the surface gravity is connected to Hawking temperature. And when the surface gravity, or equivalently when the Hawking temperature is zero, we call the horizon extremal. And we call it this way because this corresponds to a black hole having either maximal charge or maximal angular momentum or some combination of them, which is maximal with a given mass. So, so today, this is the type of near-extremality or cold black holes that I'm interested in, the ones that are either very charged or very, very quickly rotating. So why you should care about them at all? So from pure GR point of view, extremal horizons are exceptional in the usual black hole uniqueness theorems. They have a different analytic structure. They you may think about them as having different topology. So in say some Euclidean picture, so they are very different, and there are still open questions about, for example, the uniqueness. Moreover, they don't have Hawking radiation, so you would think, and you would be wrong, but you would think that maybe they have some simplified quantum description. Also, the extremal black holes are motivation for weak gravity conjecture. Weak gravity conjecture essentially tells you that you should have in your that any consistent theory that contains gravity and some U1 should have particles with charges that are larger than their masses. So, and this goes back to extremal black holes, because then these particles would be an available channel of decay for extremal black holes. From the point of view of ADS CFT holography, extremal horizons describe the infrared fixed point. So you may think about radial evolution from the boundary of ADS to the horizon as RG flow, as we move from the UV on the boundary to infrared. So by studying what are large black hole horizons and what can happen near them, we can perhaps learn something about IR of holographic CFTs. Moreover, all supersymmetric black holes are automatically extremal in Lorentzian signature. So if you care about supergravity, you sort of automatically care about extremal black holes. And also, the best examples of microstate counting from string theory are in the extremal setting, and this is when we would like to, when in certain situations it is actually possible to match gravity computation with something like Struminger-Vafa microstate counting, and this is only available at extremality. So these are the reasons why I care about extremal and near-extremal black holes.
So are IR fixed points necessarily described by extremal black holes, or it's just an example of an IR?
I would say it's an example, yeah. But it's an example that you sort of generically get in ADS CFD. I will mention a case where I mention a situation when it's not the case. Okay. Okay, one thing that will be useful is about just to set the stage, as in the introductory part, is how space-time and maybe other fields, if we have them, can look close to the horizon. So if we're near the extremal horizon, we can write our metric and maybe Maxwell field in this way. All these functions are supposedly regular at the horizon. We'll see what that means. And the fact that this is extremal horizon come up here. Horizon on this slide is located at r equals 0. I'll be sort of sloppy switching between r and rho for radial coordinate. So here horizon is located at r equals 0, and because we have this r squared here, this, when you compute the temperature, will tell you that it's 0.
So here the asymptotics of your spaceline doesn't matter?
On this slide, I don't care about asymptotics. This is just some near horizon.
So you're just dropping everything that knows about
local coordinate system. So we have this, and we can do the following one parameter family of diffeos, where we rescale our null prime v, and we rescale radial coordinate in the opposite way. So this is well-defined diffeo as long as this epsilon is larger than 0. But even though this stops being a diffeo in the limit when epsilon goes to 0, the pullbacks of the metric and of the Maxwell field have good limits. And they also automatically are still solutions to Einstein, Maxwell, whatever your GO was. But now this is just a geometrical description of what happens exactly at the horizon. And in general, what we see is that we get a very long, and in the limit infinitely long ADS to from. So for example, if I would do this limiting procedure for as an H2, I would find that this limit gives me ADS2 times S2. Okay. That's so much for the introduction, and now that's the okay. I lost something slide for some reason. Okay, and in the first part of my talk, which is based on 2 papers with Gerhardt and George Sanchez, I want to study the following problem. I have a black hole somewhere, and I have some perturbation which is stationary very far away. And this is supposed to be a small perturbation, so you may think about it as having a rocket that weighs a few tons, and I would like to understand, is this perturbation going to matter for whatever happens close to the black hole horizon? And I will restrict myself to extremal limit. This is where things get interesting, and when we can see something. And moreover, we'll see that the answer to what happens close to the horizon depends very strongly on what the cosmological constant is, whether it's 0 positive or negative, which is perhaps sort of surprising, because you would think that in a astrophysical situation, when you're just very close to a black hole, cosmological constant should be entirely invisible, but here it's actually going to give some very large effects potentially. So let me start with a very simple toy model. We have extremorized inertia, possibly with cosmological constant, and on this background, we would like to solve massless scalar field equation. So this is literally the simplest problem I could think of. And we are looking for stationary solutions. So again, you may think about it as either having some scalar source very far away that's sourcing, and now we're looking what are possible behaviors of fields very far away from this field. If we're in ADS, we may think that we put some non-trivial boundary conditions at infinity for this field, so it doesn't go to 0, but maybe goes to a constant or have some profile at infinity. And again, we want to find what it could lead to close to the horizon. So this background is spherically symmetric, so we can separate variables into spherical harmonics, and we are left with just one radial ODE that looks like this. And what is important about this ODE is that it has regular singular point at the horizon. And so we know that the solution close to the horizon is going to be given by some power law. We can just put an answer that's supposed to be power law, and here is the power that we're getting. So we actually have, as usual in this type of situations, we have two possibilities with either plus or minus here. If we choose minus here, this whole exponent becomes negative, so that means that we have a scalar field that blows up at the horizon. So this is a solution that is very irregular at the horizon. So we impose regularity at the horizon, so we would choose plus here. So we get here, and let us look at a very specific case of L equal 1 in this formula. And I'm going to assume for a moment that cosmological constant is negative. If you put numbers, you will find that as long as cosmological constant is negative, this exponent is smaller than 1. So if this exponent is smaller than 1, it means that if I take one radial derivative of the scalar field, I will get something that has exponent that's smaller than 0, so it blows up. So in particular, this component of the energy momentum tensor, rho component, blows up at the horizon. And you may think that it shouldn't matter because the very first thing that we learn in our GR course is that coordinates lie to you. And you shouldn't trust some coordinate dependent statements, and you should look for scalar quantities. Here you could compute a trace of energy momentum tensor, or maybe squared. And then you would actually find that all these quantities are finite. So that would suggest that, yeah, maybe we're just using wrong coordinates. But that's not really the case, because here this dd rho is tangent to the affinely parameterized null geodesic. So this is a component of the energy momentum tensor that has a very natural, well-defined interpretation. And moreover, exactly this component of the energy momentum tensor enters the Raychaudhuri equation that tells you how expansion of null geodesics behaves. And this is expansion of null geodesics is something physical. So this thing is actually a physical singularity, even though even though it doesn't correspond to any scalar quantity that grows. And this is going to be sort of the main theme of this whole talk, that we'll see that certain components of curvature are growing, are getting very, very large, but all scalar quantities are finite and or possibly small.
So all scalar quantities you build out of metric?
Yes. And scalar field in this case.
And the scalar field. But what about some probe that asks, what tidal forces it sees?
Tidal forces are going to be actually infinite in the extremality.
Okay, so there are physical questions for which the answer is infinite.
Yes. But this good. So to make things more precise, this is if you consider an observer that jumps into a black hole from very far away, they will see infinite tidal forces. If you would, you could consider instead an observer that's very boosted with respect to the other one, and then they would see still order 1 tidal forces.
So somebody who's near the horizon is, say, we're talking about BPS, right? Some near BPS object that's just traveling nearly parallel to the horizon. They'll see something rather benign.
Yes.
But somebody who tries to fall in from large distance
will get hit.
Okay, good.
Okay, so this was a very toy model-ish thing with scalar field. You may think that maybe some back reaction gets rid of it or so. So we want to study in a proper Einstein-Maxwell case. Oh, let me just mention that in this particular case, this goes away if you take cosmological constant to 0. So in this case, this exponent gamma becomes exactly 1. So this behaves perfectly regular at the horizon. If you take cosmological constant to be positive, gamma is larger than 1. So that means that the solution is still not smooth, but it's C1. So energy momentum tensor and curvature would be finite, but in general, you still get some non-smoothness out of it.
Well, wouldn't derivatives of curvature blow up?
Yes, radial derivatives would blow up, yes.
So why is that not as bad as curvature blowing? I mean,
Well, I would think that the easiest thing to measure is curvature, because that's what you will feel. Yeah, but sure, if you are sufficiently careful in making your experiment, you could measure arbitrary number of derivatives. So then you would always find similarity at some point. Yes. Okay.
So for instance, if I was dropping a string into this geometry, then there would be some, if I'm doing some sort of alpha prime expansion, there are some terms in the alpha prime expansion of the sigma model on the string then that are going to blow up.
I'm not so sure about that, because so all the in alpha prime you would get expansion in terms of in your action you would get expansion in terms of scalar quantities that are built out of fields.
No, you'll get curvature invariants that are dotted into derivatives of the string coordinates.
Alpha prime?
Oh, the alpha prime expansion of things like the beta function, yes.
Yeah.
But if I'm asking about the string dynamics
You're talking
itself.
about the wall sheet, you're talking about space-time.
Yeah.
Yeah.
No. Yeah. Okay.
I'm talking about the propagation of a string in such a geometry.
So for propagation of the string, it will get definitely highly highly excited. I'm not sure if this is going to be infinite effect or not, because this depends not only on the fact that you have infinite curvature, but then you need to ask about is this curvature, for example, square integrable or not, to know whether you would get infinite excitation for the string or not.
Okay.
Yeah. But definitely, at least at the moment when string crosses the horizon, it would see it. Yes.
Would you still say that GR is trustworthy?
Uh,
I mean, couldn't you construct high derivative terms in the space-time effective action for metric and phi?
Good. So for this case, you know what? I actually have a separate part of my talk which is exactly about higher curvature correction. So would you mind if we discuss it then? Okay.
It's also intuitively very weird. So you're saying if I have a tiny negative cosmological constant, so very flat space-time, I can go close to a big extremal black hole and detect it somehow. That seems quite remarkable.
Notice that we're talking here about we're talking here about sort of a global experiment, in the sense that you need to jump into your black hole from very far away as well.
Yeah, but if my space-time is very flat, I can still go very far away relative to the size of it. Also, can we go back to the scalar solution 1 second?
Yeah.
If your lambda was positive, was there potentially a singularity in that?
No, if the lambda is positive, then
That denominator by
I see. Here, if lambda is positive, you cannot have arbitrary large charge with extremal black hole. So you don't actually land into any problems in this formula.
I see. So that bound exactly ensures this thing doesn't.
Yes.
Fall.
Yes.
Okay.
Yeah. Good man. Thanks. Okay. So now we want to do this for Einstein-Maxwell, and the idea is that it seems. Oh, let me mention one more thing, that this result for scalar field was observed only locally. We only looked at near horizon dynamics. We didn't really care about what source the scalar field very far away, whether it was due to asymptotic ADS boundary or some source that we put by hand. So we still, a large chunk of this analysis will be done in the near horizon region, but then we will always at the end of the day do proper numerics to see if this is consistent in the full TO. So the idea is that it seems that we have perturbations that we sort of think should be small, close to the horizon. So we want to write our theory, our solution as near horizon values plus small perturbations, which are stationary, and it seems reasonable that if these things are small, then they should satisfy linearized Einstein-Maxwell equation. This is assumption that we're doing for now.
Could you numerically check the back reaction?
Yeah, yes, we did it. Yes. And so this is correct assumption. And so we want these things to be stationary, but this near horizon geometry has additional symmetry which corresponds to dilations. So we may also decompose our fields with respect to these dilations. So we're looking at eigentensors of dilations. So they essentially looks like this. Equation is long, but it's sort of easy. So the important thing is that there is some radial dependence in front with some power. And it's not hard to check that with this power, in particular, the Y tensor is going to behave like rho to gamma minus 2 with some prefactors here, so that if gamma is either 0 or 1, then things are smooth. But if it's not one of these two cases and rho is smaller than 2, we have a singularity here. And for people who like math for whatever reason, this does not necessarily mean that these black holes cannot be made out to be sensible solutions to Einstein equations, because even though they have some singularities, because you could think about Einstein-Maxwell equations in distributional sense, and then there would be a hope that you can that these are still valid solutions as distributions, so to the weak problem. But this also can stop if this exponent is smaller than 1/2. So if this exponent is smaller than 1/2, then these are not even weak solutions to Einstein-Maxwell equations.
Does weak mean you could form these from some?
Weak in the sense of distributions that if you then multiply them by some smooth, compactly supported things. Yeah. Okay, so this is actually very easy computation on Reisen-Inertium, because Reisen-Inertium is spherically symmetric, so we can decompose everything into spherical harmonics, and in this way we actually taken care of all coordinates, and we are left with just algebraic problem to solve. These are not even ODEs; these are just algebraic equations that we can solve, and we're finding 4 branches of possible exponent. 2 of them are very badly negative at the horizon, so we remove them by regularity, and we are left with 2 other. And here, the most interesting one is this red curve that corresponds to L = 2 mode. And as you may see, this is always smaller than 1. So going back to the previous slide, smaller than 1 means that definitely we have tidal forces that blow up. And they actually blow up sufficiently fast that they're also not integrable. So it's not only that you will feel discomfort when you cross the horizon, but the actual change in momentum of your particles is going to be infinite on the other side. And moreover, if you go to sufficiently large charges in ADS units, you find that these exponents also become smaller than 1/2. So then you cannot think about these as distributions as well. Okay, so this was all in strict extremality, but strict extremality is perhaps maybe too special and also very hard to probe numerically. So it's actually easier to work with nearly extremal black holes and then systematically lower the temperature. And then if you are sufficiently close to extremality, there is still a huge near horizon region in which spacetimes pretty much looks like ADS2 times S2. And things should behave the same way, so we should still have these power laws and so on. But then at some point this region must end, and then it must sort of smoothly caps up. But if it's smooth, then we would expect that fields shouldn't change too much between the ADS2 region and the tip of the cigar, and so the result should be sort of similar. In particular, the Weyl tensor should be still large when evaluated at the horizon. And then you can argue that, in fact, this component of the Weyl tensor is going to behave like T to exactly the same power as was radial dependence in strict extremality. And this is going to be the best way to actually probe this numerically. So here are the results. This black line is analytic prediction, and these blue points are results of numerics. This is as a function of temperature. Here we have a maximum of tidal forces. So as you may see, this is a very good fit. We got a difference on the fourth significant figure.
Sorry, I got a little lost. So this is some Weyl tensor under what? Under some perturbation of the...
Oh yeah, good. I didn't say. Thank you. Yes. So what we do is we turn on a small perturbation in because we're in ADS. We change boundary conditions. What we do is we change boundary conditions for Maxwell field, and we start and then
conditions at infinity.
Yes, at infinity. At four-dimensional at infinity of ADS4, and then we look for stationary black hole solutions inside with prescribed temperature.
So when you change the boundary, so is this the change correspond to what people usually call nearly ADS2 boundary conditions?
No, I'm talking about boundary conditions for ADS4. I'm putting some spatial profile for Maxwell field at infinity.
Okay.
But you're solving the Einstein-Maxwell equations?
Yeah,
'Cause you're
nonlinear.
going back-
This is a result of nonlinear computation.
And what, you're not changing the boundary conditions for the metric, or?
For this part, this result is sort of generic. That generically whatever change to boundary conditions you do, unless you kill something by symmetry, you will see this behavior. In this particular case, we modified boundary conditions for the Maxwell field. So this is still Dirichlet boundary conditions, but now Maxwell does not decay. AT does not decay to a constant, but to some function of fineness. Okay. So this was in 4D. And now we can go.
So I'm sorry, I'm still a little bit confused with what the takeaway is. So is this an instability?
No, this is not.
This is just a distortion of the near horizon geometry.
Yes. The near horizon geometry actually does not change. This is the first step away from near horizon geometry gets changed in this context. And what we were seeing is that if you are very sufficiently close to extremality, it's going to change drastically. That even if you put a very small perturbation to your boundary conditions at infinity, you get a very large tidal forces at the horizon. And this is something sort of specific to ADS that if we go. So I told you that this red curve was the main troublemaker. If we were in de Sitter, this curve would instead go from 1 to larger values. So it's still smaller than 2. And if it's smaller than 2, then it still means that we have a singularity. but this singularity is, for example, now integrable along the geodesic. So you could cross the horizon, you would feel sort of distorted, but the actual change after but you could survive this process. In ADS, you wouldn't survive. And if you go to asymptotic flat limit, if you kill cosmological constant, then all these exponents for all the modes become exactly integers. So that in without cosmological constant, you can put on some source very far away, but you would get perfectly smooth solution everywhere.
Okay, and is this so did you stop looking when you reached the outer horizon, or can you follow this all the way through to the inner horizon and see something worse happening there?
Yeah, we mainly stopped looking at the outer horizon. In general, this is essentially because this behind the outer horizon, it's no longer an elliptic problem. So you just need different numerics to run there. I think, well, based on some other examples in the literature, I would expect. I think you would find that you develop singularity inside. And that sort of in the limit, this singularity goes to.
So you're seeing sort of like a tail of a singularity that's further inside. Okay.
Yeah. Okay, so now we can play the same game in 5D. So if we now don't have cosmological constant, we'll find that generically the metric is going to be C0, but not C1. So what it corresponds to in previous slide was that this gamma exponent is equal 1/2. But something much more interesting happens if cosmological constant is negative, because then we have exponent that is actually negative. So previously we had 4 exponents, 2 were negative, 2 were positive. We could get rid of, we could kill 2 of them by irregularity. Now we have 3 negative exponents, so we cannot kill all of them. And this suggests that if we change the boundary conditions ever so slightly, we would go to a very different near horizon geometry. So previously, near horizon geometry was the same, but if we stepped away from it, things happened. Here, even near horizon geometry is going to be different, even if it exists. And the same is also true in higher dimensions, even without the cosmological constant. Okay. So I previously, at the very beginning, I told you that these near horizon geometries are supposed to describe infrared fixed points. So that's so if it's the case that if we slightly change the boundary conditions, we fly to a different IR, that means that the fixed point that we started from was RG unstable. That we could, and that renormalization flows put us into something else. So we would like to find new, perhaps hopefully stable fixed points. And so we need to do it, we need to solve these 5-dimensional near horizon geometry equations. And we already know one solution that's unstable, namely Reis-Nordström ideas. And so the question would be, can we perturb it and see something better out of it? And you can check that.
Sorry,
Yeah.
I just got a little lost on, what is it that you're now, I mean, you've just said that there are no static regular solutions.
Yes.
But now what's the further, I just got.
Okay, sorry.
I got lost on what the further thing you're doing now.
So here we expect, so in 4D what happened was we changed boundary conditions and we found large infinite tidal forces in the extremal limit. Now we're finding that if we change boundary conditions, we get a totally different geometry. And we would like to of the horizon itself. even without asking how the geometry looks outside the horizon. So now the first step that we would like to do is to try to understand what are possible geometries of the horizon itself. So we started from, without perturbation, we had S3 times ADS2, and we would like to understand what are possible deformations of that geometry.
Okay, so you were just doing the linear, in getting the blow up, you're doing linearized.
Yes, and now I want to solve full
now you're doing the full
equations, but
linear with I mean the
yeah, but only at the horizon. Okay. Thank you. So you can check that if you try to linearize to perturb this resonance medias, that you find solutions only for some discrete values of charge. And if you expand around them, you can perturbatively build new horizon solutions, and then you can do it even nonlinearly using numerics. And then this particular value of Q tells us what's the angular moment, what's the angular number L that we're turning on. And in general, we constructed actually a large number of new solutions with different symmetries. So we find solutions with SL3 symmetry, U1 times C1, and also without any symmetry. In general, it seems that there is an infinite number of new fixed points. But for obvious reasons, numerically, we're only able to find a finite number of them. But in general, we have an algorithm how to find all of them.
Why? What chooses these particular values? It seems weird that you're looking at solutions and saying that you only get an interesting result for some particular value.
Yeah, we'll see that this is not the right thing in a moment, actually.
Okay.
But the thing is that you can compute for various various spherical harmonics. You can compute these exponents, and all of them at some point crosses zero. For some particular charge, they cross zero, and when they cross zero, you can build this new perturbative solution.
Is this some kind of Gregor-Liflaum instability for some statement that like the horizon wants to localize on this S2 or S3, whatever it is that you have?
To some extent, yes. Let me maybe go through this. And
why don't you present
it?
it?
Yeah. Mm-hmm. Okay, so here we find solutions, some examples of solutions with L equal 4 and L equal 5 and 6 and 7. Again, we build them perturbatively around given new horizon, around ADS2 times S3 new horizon geometry, and then we turn on numerics to do a better job. But all of them are still unstable to changes of boundary conditions. So this is not something you would generically flow.
Unstable means, just so I understand, you're looking for stationary solutions and you're getting singular behavior at the horizon, as opposed to you're giving initial conditions and seeing that things are blowing up in time.
Mm-hmm.
Okay.
Yes. So these are not the generic IR fixed points that you would flow into. You perhaps with enough fine tuning, you could flow into them, but this is not generic. Maybe given time, let me skip and say that instead what we actually did was we perturbed solution with Q equals 0. So this is actually a singular solution, but you can still do singular perturbation theory around it and to some high order, and then again put on your numerical hat and get some solution. So let me show you how it behaves. And the thing is that now this thing is stable under small perturbations of boundary conditions.
Wait, where are you saying the boundary? This is lambda equals 0 case? Or...
I'm sorry?
This is lambda equals 0?
No, this is negative lambda.
It's still negative.
Yes.
Okay. So,
yeah. because here we are interested in understanding RG flows of the boundary theory. And the interesting thing that happens is that we're actually finding that these new IR fixed points that seems to be in some sense more stable, they actually have lower entropy than spherically symmetric ones, which is sort of interesting from the dynamical point of view, because that means that if you started at extremal horizon inertium and you turned on at some point some profile for your boundary conditions, and you would look how things evolve, you wouldn't evolve into this. Because what we think happens is that to change these boundary conditions close to extremality, you need to put some energy into the system in a way that you go away from extremality. But that's just an aside comment. How these solutions look like is that they quite flattened. So at first we call them pancake horizons, but actually if you go to sufficiently large charges, they're not even flat, they actually have negative curvature at the poles. So they have positive curvature around the equator and negative curvature at the poles. Okay, here's again how they actually look like if you try to embed them. And if you now consider these solutions were SO3 symmetric, and if you now try to check if they're stable under these small changes of boundary conditions, you find that they are stable, provided that your perturbations respect this SO3 symmetry. But they are still unstable under more general perturbation. And so for entirely generic boundary conditions, these are still not the right solution. And in general, numerical search so far suggests that there is no near horizon geometry that could be RG stable, that would be stable under all small deformations of the boundary. And right now we don't know what the right picture is. But let me maybe mention here one paper by George Santos and Will Biggs when they showed that you can find, if you have these deformed boundary conditions, you can actually find a solution in ADS with two black holes. And it seems that there is no reason why you could, this was in ADS5, and it seems that there is no reason why you couldn't find a solution with 3 or 4 black holes. And if you look at, oh, actually I don't, sorry. And in general, what you can find is that smaller black holes are sort of more resistant to changes in these boundary conditions. So the relevant conformal dimensions are going closer and closer to marginal instead of relevant. So it is possible that the right fixed point is actually not given by one black hole without any symmetry, but instead it's given by a large number of very small black holes. But that's right now just a conjecture. Okay, so now we are leaving ADS and we're going to real world. So no cosmological constant, but instead of cosmological constant, we will have electrons. And I'm told these actually exist. And in general, GR is, we believe, actually some low energy description of whatever the fundamental theory is. And instead of trying to come up with what the right string theory would be to describe them, we can try to do a bottom-up approach and just parameterize higher derivative corrections. And the first non-trivial terms for Einstein-Maxwell's are given by the following 3 coefficients. In general, you would have more terms, but you can kill them by filter definitions. So these are the only 3 filter definition invariant terms. And we can ask what happens with extremal Kerr-Newman in this theory. Oh, sorry, one thing I should have mentioned and didn't, is that although I presented results for horizon inertium, these results were sort of generic. If you take on Kerr or Kerr-Newman, you see qualitatively the same type of behavior. And in particular, when you turn off cosmological constant, everything is smooth. So these singularities and so on were something about having a cosmological constant. Okay, so now we would like to, it seems that asymptotic flat black holes are sort of fine-tuned, and we would like to see if we go away from GR and turn on higher derivative corrections, whether this fine-tuning will go away and we'll see something interesting. Okay, let me give you rough estimates. So we want to take these coefficients to come from actual electron loops in QED, and then roughly speaking C7 and C8, so these were terms that were F4, behaves like Q over M to the fourth times some coefficient, and C6, which was a mixed term, behaves like Q over M squared. And for real world, in the units we're using, Q over M for electrons is actually ridiculously huge. This is 10 to 21. And then based on dimensional analysis, we would expect that the scaling dimension would be given, that the change of the scaling dimension, which is dimensionless, should be given by this coefficient, by this Wilson coefficient times Q over M times the following combination. And we know that C7 or C8 is quite large. And so then the curvature actually, because we're perturbing these exponents. We saw before that whenever whenever exponent is smaller than 2, we get singularity. But here for Kerr-Newman, we have exponent that's exactly equal to 1. So if we perturb it just a little bit, this will introduce singularity. But this singularity will be suppressed by gamma minus 1 that's set in front. So val is gamma minus 1 times t to gamma minus 2. So this will behave like this guy will be shift in the critical in the exponent over temperature. Okay, so this is what we expect, and here are the numbers that appear. So Q over M is going to be very small for real world black holes, but on the other hand, we have this crazy 10 to 81 coefficient in front. So you can ask whether it's large or not. Let me mention maybe that because at the very beginning I mentioned that there are also various quantum gravity effects that are important for near-extremal black holes, and these quantum gravity effects are important when this denominator is roughly speaking of order 1. But here we have 10 to 81 in front. So this is why this thing that comes from QED is way more becomes important at way larger temperatures than quantum gravity effects.
Is this a reliable calculation? So if 5 is large, if 5 is in fact, equation 5 is in fact large, is it a reliable calculation?
Good. So first of all, I would say that this really tells you that your EFT description is breaking down. And I would say that it breaks down not when it's even large, but when it's of order 1, this change of the...
So what is the thing that is breaking down? Like what illegal move did you do?
I mean, what we're finding is that there is an observable such that it gets large corrections, even though you don't have any large terms in your action.
This I understand, but suppose we just integrate back in the electron.
Yes.
So if I just have Einstein, Maxwell, and a dynamical electron, will I get well-behaved theory, or is even that have
this I don't know, because this is hard because this comes from loops. So this is really quantum effect, but there is a different version of doing this computation if as a source of these higher curvature corrections would have an axiom instead of
I don't understand the electron, the Einstein Maxwell. I mean, is this a dynamical gravity effect? Like you're just considering Einstein Maxwell sorry, you're considering QED on some fixed gravitational background, right? Why do you need, where is the strong effect coming from? Why can't we use the weak coupling of QED to control the calculation?
We can. This is weak coupling computation.
But where is the breakdown of EFT then? Why would that break down? I don't understand.
Let me give you an example of a different EFT, or of a different source for this EFT. Okay, if instead of doing QED we had an axion that's coupled to Maxwell field through dimension 5 operator, and then we can integrate it out if it's very heavy, and we would get the same type of higher curvature corrections. Okay. And so now we also checked what happens if you don't integrate out the axion, and you still get this singularity. So this singularity would be for at least for the axion is already present at the tree level.
I think what Clay is asking is, you're getting these effects by looking at some loop of electrons with some graviton legs hanging off of the loop.
Photons mainly, but
photons, graviton, whatever. And so, okay, so there's some loop diagram with some number of insertions of gravitons and photons, and you're saying it's 10 to the 81. So on the other hand, the electrons are just propagating around in this geometry that you say is relatively smooth. So why are those loops enormous? What are the electrons seeing that?
But okay, so these coefficients come actually. This is flat space computation. This was not. This was no. We didn't this computation on Kerr-Newman background even. This is just what you get in flat space time. Simply because you have now four photon vertices. Each one gives you a factor of Q, and you have 4 electron propagators, which one gives you 1/m. So this is where the scaling comes from. And it just happens that in Planck units, this is a very large number.
If the black hole is much larger than the Compton radius of the electron, how could the correction be large if the correction to Maxwell electrodynamics is suppressed by the ratio of the length scale, the Compton wavelength of the electron to the length scale in the problem, which is the radius of the black hole. So are you saying that this correction is this formula, equation 5, give you something small when the radius of the black hole is much larger than the Compton radius of the electron?
Not necessarily, but so the reason why we're seeing a large effect is because very generically extremal black holes want to be singular, and it just happens that Einstein-Maxwell without a cosmological constant is a very fine-tuned theory, such that you don't get these singularities. So what we're seeing here is that you're adding a small correction to something that was very fine-tuned. So it's no longer fine-tuned, and this is why you discover that you have large effects. Just like you would see that you have singularity if you take Rising-Nystrom ADS with very small negative cosmological constant, you still see this singularity, even though it is naively you would think it shouldn't matter because it's much smaller, because scales there is a hierarchy of scales.
Is there an energy scale suppression in 5 somehow? Just coming back to Son's question, like if you look at, is there some way to look at lower and lower energies in this observable and see that this effect goes away, or is that not true?
Yes. So this is good. So what this guy really measures is the tidal force that you would feel if you would jump from very far away to Kerr-Newman. If you instead started close to the horizon and locally you would have energy of order 1, this would be small. So this is, so maybe a way to say it is that you get that this is a small effect, but this small effect works for a very long time because you have a very long radius to float. And this amplifies these higher curvature corrections.
Somehow the statement that Kerr-Newman is not classical cannot be reliably studied classically.
For certain observables, yes, I think that's it's sufficiently close to extremality.
So suppose I have a black hole with some charge.
Yeah.
And then I wait for it to completely radiate, Hawking radiate. Temperature goes to 0. And so how do I describe it if the correction to Kerr-Newman is large?
Okay, so here actually this particular correction, it's important that it's Kerr-Newman, not Reisen, not Schur. And so for Kerr-Newman, what would happen is that you would preferentially Hawking radiate angular momentum first. So you would actually go away from extremality. So you could still imagine that, by enough work in initial data, you could create near-extremal Kerr-Newman, but actually waiting for a very long time is not the right thing to do. Okay, but you may say that I promised you that we're going to real world, and in real world, black holes do not have charge. But actually they do, and I guess I may assume that everyone knows how they get charge in realistic situations because it was Bob who came up with it. So let me just very quickly say that it is because we have a rotating black hole that is embedded in magnetic field. And also in electrodynamics, if you would have some surface that's embedded in magnetic field, close to the surface, it would look like there is electric field as well. And this electric field in practice could be used to charge this black hole. So for example, for supermassive black holes, using realistic values of magnetic fields, we can get Q over M of order 10 to minus 12. But if we would consider a black hole that merges with a pulsar, then for a short time, it would experience a very large magnetic field. And then assuming that you can trust this computation, and it's not obvious because now it's a very dynamical situation, but assuming you would trust it, you could actually get Q over M that's of order 10 to minus 7.
So you had a z squared, right? The previous expression.
Yeah, z to the 4th.
Okay.
Yeah, so this is going to be very small, but even if you take z to be of order 10 to minus 12, which is entirely realistic thing, then you get 10 to minus 48. This is multiplied by this guy.
Still gigantic.
No, actually it's not, because here you have mass and entropy. These are large numbers. So for realistic black hole, this is actually small. But if you say I don't care about real world, I'm a theorist, I can create a black hole that has sufficiently low temperature, then you could make it to be large. But it's definitely larger. This prefactor is definitely larger than prefactor for any quantum gravity effects, for example. So this is leading beyond Einstein-Maxwell correction. Okay, you can ask also how close in real life we could go to extremality, and the general astrophysical bound is given by Thorne, and that tells us that A, so A is angular momentum over mass, must be smaller than 0.998, and in fact we are actually relatively close. So for example, for Cygnus X1 we can get this to be of order 0.9, and recent LIGO observations would again give us something of order 0.9. For surprisingly heavy black holes, shouldn't exist. Okay, so given time constraints, let me maybe quick up a little bit, and the estimates that you get at the end of the day are the change in the Weyl tensor, for example. So this is normalized, is going to be 10 to minus 8 to 10 to minus 6, depending on how close you can get to Thorne's bound, times magnetic field over 10 to 16 Gausses. So best case scenario, this guy could be a further 1. So this would be in real life, in very, very best case scenario for the 1 in a million.
Sorry, what is the left side there?
Yeah, good. So this is C bar is this component of the Weyl tensor for just Kerr-Newman, and C is the corrected version. So this is how Weyl tensor changed with regard to the background values. So best case scenario, you can get this to be 10 to minus 6. More realistic, probably 10 to minus 10.
I'm sorry, how does the magnetic field of a magnetar come in?
Good. So we're using this magnetic field to estimate what's the charge.
Oh, okay.
Yeah. Hey, so as I said, at the end of the day, yeah, we're not going to see it, but if we were ever to see something from near-extremal black holes, this would be the thing we would see.
Do you count this as a quantum gravity effect?
No, I don't. Yeah, maybe I shouldn't say any other quantum gravity. No, this is, as I said, this is QED effect. Okay, let me skip it and go to the, how much time do I have?
0, but let's call it 5 minutes.
Okay, just very quickly, let me, yeah.
Sorry, I'll ask.
Just very quickly, let me go to the last chapter here, that what happens dynamically. So you can ask, what happens if you perturb a black hole by a small time-dependent perturbation now? And where naively you would think that some part of it will fall inside, some part will escape to infinity, and that's it. After a long time, you wouldn't see a sign of this perturbation, and hey, you would be right. This is what really happens, except for extremal black holes. So Artekis showed that if you just consider mass as scalar on resonance background, then at late times, this scalar outside the black hole decays with all its derivatives very quickly outside. But on the horizon, it decays like 1 over v. V is proper time, affine time on the horizon. But the first radial derivative on the horizon actually approaches a constant at late times. And then the second derivative actually blows up at late times. So in particular, energy momentum tensor at late times goes to a generically non-zero constant at the horizon, but is 0 outside. And these results were generalized to any other linearized theories on extremal backgrounds and seems to be a very generic fixture. However, this requires a lot of fine-tuning, because what would happen if you turned on back reaction is that something fall into a black hole, into an extremal black hole, so it's no longer extremal. So then this effect would go away. So what you can see in practice is that you get behavior like this for a very long time, and then after some time things really just decay. But in ADS, we can consider planar black holes, and planar black holes have infinite energy and infinite charge. So if I take this infinite energy, infinite charge black hole and put some finite energy perturbation on top of that, this won't change the temperature because it's infinite energy versus finite energy. So here we could stay extremal even with back reaction. And here I will focus on ADS5 because this effect is slightly larger in this case. At the end of the day, what you can find is that the ratio, if you have a field that has satisfies some wave-like equation on this extremal background, this is for now linearized, then this field will decay like V2 minus alpha, where this alpha is a conformal dimension in ADS2 of the near horizon geometry. So in particular, it would depend on mass, on whatever. Okay, and now we can write Einstein-Maxwell equations, linearized ones, in terms of some gauge invariant quantities that satisfies this type of equation. And from them, we can build Weyl tensor by taking two derivatives. And if you look at the profile I showed before, you would see that if you take two radial derivatives on the horizon, this will give you behavior of order V2 2 minus alpha. So if alpha is smaller than 2, so if conformal dimension is smaller than 2, that would mean that tidal forces would actually grow on the horizon instead of decaying. And moreover, they will be large outside the horizon up to or radius of order 1 over time. Okay, we can find here what I have is an effective mass in ADS2. So you need to translate it into conformal dimension. This is for Einstein-Maxwell, ADS5. And what is important here, that there are two solutions, plus and minus. Plus is boring, minus is more interesting. And what is interesting about minus is that, first of all, this mass can actually go negative. It's above two-dimensional BF bound, but it's negative. And moreover, if you were in dimension 5 or higher, then this guy has becomes the most negative on non-zero K. So that means that the mode that is most relevant from ADS2 point of view, or the mode that will have the fastest growing tidal forces, actually occurs at some non-zero wavelength. Okay, and here is how it looks numerically. So here we're solving nonlinear Einstein-Maxwell equations in ADS5 with dynamical perturbation. These are tidal forces, and you may see that they grow. This actually becomes negative, but it means it's growing. So they grow at late times around some specific wavelength that's determined by local charge density. So effectively, what happens is that at very late times, your near horizon geometry goes to just ADS2 times R3 in this context. But if you look at curvature instead, you get a lattice of a lattice in curvature that's with wavelength given by this part here, this line here. Okay, let me summarize that in general, your generic extremal black holes are not smooth. And it's just a coincidence that a few examples that we know analytically are smooth. Moreover, resonance in 5D IDS5 is not RG stable. If we change boundary conditions just a little bit, we will change geometry drastically. If we look at Kerr-Newman with higher curvature corrections, the curvature becomes large, close to the horizon. So your effective field theory breaks down there. And planar black holes, when you perturb them by finite energy perturbations, develop large curvature lattice, if you want, at late times. Okay, that's all. Thank you.
I have a question. Can you go back to the summary slide?
Yeah.
So perhaps you said it, but what is the holographic interpretation of the fact that Verizon Nordstrom ADS5 is not RG stable?
That means that this is not the correct IR for whatever is going on the boundary. It's not Yeah, so far we don't actually know what is the right fixed point. Whether it would be given by this geometry fragmenting into smaller pieces, or maybe you would emit some d-branes and just 5-dimensional perspective wouldn't be valid. This is not clear, but definitely, but definitely the upshot is that you shouldn't trust it to describe your IR.
How sensitive is that statement to the actual ADS5 that appears in string theory with all sorts of extra fields, various scalar fields and so on?
Good. So in this case, I think you would find that your ADS5 actually wants to emit different branes. These are dual-dressed black holes. And then but first of all, to describe them, you really need to have ADS5 times S5. And then I'm not sure what's the right picture for whether these things go through or not.
You mentioned toward the end talk that back reaction should stop the Aristakis instability or something. Is it known what the nonlinear effects do with the
Yes. So there is numerics on that generically you get Aristakis-like effects for a very long time, and then it decays in the way that's just governed by quasi-normal modes.
But then what does the extremal black hole evolve to? I mean,
it evolves to non-extremal black hole. Just that. There are cases, I have some citations here. Oh, no, I don't. So there were recent results that showed that you can fine-tune your data in such a way that you actually stay extremal. And this was first done by Harvey Real and collaborators in numerically, and recently by some mathematicians analytically as well, that you can stay extremal and then you have Aristakis instability for all times. But generically, you just evolve to non-extremal resonance. Well, probably more generically to Kerr-Newman, but within the symmetry assumptions they work with, it was just right.
Any further questions? All right, thanks, speaker again.
It's Aristakis.
Yeah, so,
This is for uncharged.